Okay, so we've just talked about not, and so now let's talk about implies. And so the idea here is that we want to make this implies arrow, and this is really a kind of logical operation. It's a arrow from omega times omega to omega. But there's various gadgetry related to this, and there's some pretty interesting kinds of relationships that we're going to see with these Hom functors and subobject classifiers in set to the power of c. But let's begin by recapping the sort of general definition of this stuff in an equalizer. So we have this sort of relation on omega. In other words, we have this subobject of omega times omega, which is called less than or equal to 1. And this is defined as the equalizer of P1 and AND. And so this is going to be a subobject of omega times omega. We think of it as a monomorphism emanating from an object which we just sort of arbitrarily call omega 1. And then this is obviously a subobject of omega times omega, so it has a classifying arrow, and we call its classifying arrow implies. Okay, this orange arrow here. So this is a sort of logical operation. Now, here's some interesting relationships which I go over in much more detail in my video on sort of general topos theory, topos theory essentials. But just to say briefly, how does this stuff interact with arrows? How do we use it? Well, here's a very sort of important few results. Suppose we have subobjects R and Q of X. Well, then we can form their classifying arrows, and we can find a kind of productive pair of them into omega times omega. And now what we're going to have is implies after chi q comma chi r sends everything to true. By the way, let me just say this is usually written as chi q implies chi r. So often that arrow is kind of shifted into the middle as an infix operator instead of a prefix operator, but this is the proper way to write it. Anyway, that's going to happen if and only if, well, this is just the same expression, but we've replaced this arrow with what it really is, which is the classifying arrow of less than or equal to 1. So this happens if and only if less than or equal to 1 of chi q comma chi r is equal to true after exclamation mark x. And now this happens if and only if chi q comma chi r is in less than or equal to 1. And this happens, since less than or equal to 1 is the equalizer of this stuff, this happens if and only if doing P1 on this gives the same result as doing AND on this. So it happens if and only if chi q is equal to chi q and chi r. And now these are arrows into omega, so now converting into the kind of sub-objects that they classify, we see that this happens if and only if q is equal to q intersection r, and this happens if and only if q is contained in r. All right, so you see basically, and it makes sense. I mean, think about in set, for example, if the classifying arrow of Q is active, implies the classifying arrow of R is active, that's essentially saying Q is contained in R. And we see the same kind of result is true in a general topos. Okay, so we have all this stuff now. So we want to kind of visualize it. And the first thing is, how do we compute this relation here, less than or equal to 1? So it's a pretty mechanical process. We just draw out P1 and P1 and AND as arrows from omega times omega to omega. And then we find out the kind of equalizer of them. So it's a bit laborious, but we can do it. So here's omega times omega at the top here. By the way, I think previously I had a little typo. I had an M here where I should have had a false. Anyway, I've corrected it now. So, you know, we just draw the P1 arrow, which is shown in green, and the AND arrow, which is shown in red. And then we want the equalizer of those two arrows. So we just want all of the kind of loops and vertices which get mapped in the same way under these two arrows. So once we actually work that out, we find that this kind of sub-object here of omega times omega is what less than or equal to 1 is. And you see essentially it's selecting the pairs where the first entry in the pair is at least as true as the second entry in the pair. And you see here that it's selecting the pairs such that the second entry in the pair is at least as true as the first entry in the pair. And this makes sense with our general kind of intuition of false. So false implies true, that's okay. False implies false, that's okay. True implies true, that's okay. True implies false, that's not okay. So that's outside of less than or equal to 1, because that's not true. And similarly with these loops, but we've got M's here. And we can, in this kind of thinking, we can essentially think of the psi M's as something that's kind of intermediate truth value between true and false. Okay, so this is a bit fuzzy, but we can sort of say that psi true is at least as true as psi M, and that's why this loop here is present in less than or equal to 1. In fact, we'll see some more intuition about this later. I'll just rub that out for now because I'll get onto that later. But you know, we can make this more concrete. This sort of, we can really understand the essence of this less than or equal to 1 sub-object of omega times omega, and it's pretty interesting. So okay, we've understood now what this less than or equal to 1 kind of arrow is, at least in the category of functions. What about this implies arrow? Well, that's simply the classifying arrow of less than or equal to 1. So we can just compute that classifying arrow. So essentially, it's just going to send all of the loops which are in this kind of sub-object less than or equal to 1 to true. These loops which are sort of have their vertex in less than or equal to 1 but are not themselves in it, they get sent to psi M. And the other stuff completely outside of less than or equal to 1 just gets sent to the false loop here. Okay, so that's what the actual implies arrow looks like. So I'm going to talk about some kind of theoretical results now, and you can find them in the video attached in the description called Containment and Implies Proofs. Anyway, so you remember from this kind of logic here that, you know, saying that implies operating on two things sends everything to true is really just equivalent to saying that the kind of sub-objects classified by those two things involved, the first one's contained in the second one. All right. So this is really the important thing. Well, it's the simplest thing that we can try and get our heads around. And we can ask, well, what does this mean in set to the power of C? What about if Q and R are just containment monics? Is there a nice simple way to understand what it means to have one of them contained in another when they're both inclusion monics? And indeed there is, and it's pretty much just what you'd guess. So when little q and little r are inclusion monics in set to the power of c, we actually have q is contained in r if and only if capital Q of E is contained in capital R of E for every E in C. So here, of course, these are just sets, and we're just saying that every E-type element of capital Q is going to be contained in capital R, and that's equivalent to saying that little q is contained in little r. So, I mean, this is really just saying that saying one sub-object is contained in another in set to the power of c works just like that kind of statement doesn't set. It's just that, you know, things might be higher dimensional and stuff. So, yeah, the proof to this is in this description. Here's some other interesting kinds of observations, and it's kind of intriguing. The way we defined omega of E, we have this funny thing where we're sort of simultaneously thinking of the elements of omega of E just as elements of omega of E, but also as kind of sub-objects of Hom E comma blank. Now, notice we don't have to do that. But I mean, essentially what we have is that an element of omega of E, I mean, really, the actual thing it corresponds to over here is theta under arrow star. That's really the kind of sub-object of Hom E comma blank that it's corresponding to. But essentially, we're just sort of identifying those things because the thinking goes along the lines of, well, we don't really know what to call these things. We know how to compute these things. We know how to make sense of them. We know that this is just a set of stuff. So why don't we think of the elements of the set literally as this? And it doesn't really matter in practical terms, but you know, it's worth bearing in mind that really we ought to be thinking that there's some isomorphisms at work. Anyway, the point is that there's some sort of interesting interpretations of these different logical operations in how they play with these kind of elements of omega of E. So, for example, we have our terminal object and we have omega, and we've already seen these two special arrows, true and false. And amongst the sort of results which we've kind of obtained so far, we have this one, really, which is saying that if we have an E-type element theta of the terminal object, then the E component of true, so of course E is an element, of course E is an object of the category C, but anyway, we have that doing the ETH component of true on theta really sends that theta to the element of omega of E corresponding to the maximal subobject of Hom E comma blank, and also doing the ETH component of false on that theta sends that theta to the kind of element of omega of E corresponding to the kind of empty subobject of Hom E comma blank. But this kind of interesting relationship goes much deeper, and we can also think about how the other kind of logical operations work. So we also have this thing I call the AND lemma, which says in set to this E, suppose we have a couple of E-type, suppose we have an E-type element of omega times omega, so it's a pair, alpha comma beta, in this set, omega times omega of E. Well then, what happens to this when we do the ETH component of AND on such a pair? Well, we actually interestingly get alpha intersection beta. Okay, and this is obviously considering this as a subobject of Hom e comma blank. So this is pretty interesting. I mean, it's more of academic interest to us at the moment, because, you know, there's a lot of other results which we want to get at for sort of actually being able to do computations in set to power of C. But this is sort of an interesting result worthy of further exploration. And here's another one of a similar kind of level. This sort of implies lemma. So if we've already discussed this less than or equal to 1 subobject of omega times omega. And then if we want to think of it as an inclusion monic, then what are the E-type elements? Well, there'll be the set of pairs alpha comma beta such that alpha is contained in beta. All right, so these are pretty interesting results, and you can find the proofs to them in this attached video, containment and implies proofs.